Hello and welcome. This is question 2 for Edexcel's M1 June 2003. What I've done here is I've drawn on the scenario that is explained in the first paragraph. Okay, so we've got this particle A and particle B. Particle B has a mass of 0.08 kilograms and particle A has a mass of 0.12 kilograms. We're told initially they both have a velocity, both stationary, a velocity of 0, in other words, both stationary. Then A accelerates, A accelerates to 3 meters per second, okay, and therefore it collides with B, okay, and then after this collision, A has a velocity of 1.2 meters per second. They're in the same direction, okay, so basically they've collided and then it should push B a bit further, so obviously B's got a high velocity, or it should have at least, okay, otherwise it'll keep colliding. Okay, and the first question just asks us to work out the magnitude of this impulse, stating clearly the units in which your answer is given. So really, in essence, it's asking us to work out the change in momentum of A, okay, because obviously we know that momentum is the, impulse is the change in momentum, okay? So really, the thing that they want you to do for this is obviously, the first thing that you would state is impulse equals change in momentum, or delta momentum if you're writing it fancy, or can't be bothered to write out the full thing. Okay, so initially, so this is before the collision that it gets when it hits B. Okay, so we need to work out the change in momentum from it being. So God's sake, that one over there. See, that's pretty good. Anyway, we need to work out change in momentum from A being stationary to reaching this 3 meters per second. Okay, so really, what you want to do, change momentum, is momentum after take the momentum before. Now, obviously, we know it's momentum is mass times velocity, and if you have a velocity of 0, then obviously you're going to get a total momentum of 0 after, before. But because we still need to encounter it in terms of, in case it wasn't 0, we still need to show that we're using the same method, okay? So really what I would do is still write it in. It's not going to take that much more time. You probably more time complaining about it, and you could have, wrote it down. Anyway, so it's momentum after take momentum before. So the momentum after is, well, it's 0.12 kilograms times velocity of 3 meters per second, okay? And then you take away from that, obviously, 0.12 kilograms times 0 meters per second, which is the same as, obviously, 0.12 kilograms times 3 meters per second, which obviously therefore gets you 0.36. And all we're doing is sort of adding the units together because we're times in kilograms by meters per second, so we get kilogram meters per second. Okay, so that's why it's asking for the units as well. It's obviously a units mark as well. So you get a mark for the right answer and a mark for the units. Okay, so that's what the 2 marks for. And then what I'm told, immediately after particles collide, the speed of A is, what I've wrote down here, is 1.2 meters per second, in its direction and motion being unchanged. Find the speed of B immediately after the collision. Well, the only thing that we can apply in this case is the conservation of momentum, which states that the momentum before will equal the momentum afterwards. Okay, in other words, there'll be no overall change in momentum of the system. Okay, so what we need to do is encounter the fact that B's initial speed obviously was 0 meters per second, and we need to find its new speed. Now, we can't take A's initial speed as 0 meters per second. What we need to take A's initial speed is just before the collision, okay? Which was at this point here, which is sort of why I've drawn 3 scenarios when I could have really just drawn 2. Okay, so just as it hits B, its velocity, or what we'll call the initial velocity, is the 3 meters per second, okay? So it's always a good idea. You might want to split it up into sections, so, UA is the initial speed of A, which we know is 3 meters per second. And the final speed of A, which we also know, V subscript A, is 1.2 meters per second. Okay, and we know the initial speed of B, so UB, we know that was at rest, so it's 0 meters per second. And all we have to find out now is the final velocity of b, or v subscript b, which I'm just going to put as v meters per second. Okay, so obviously we know the mass of b and the mass of a. You could write that down as well. So the mass of m1, we'll call that the mass of a, okay, which is 0.12 kilograms, and the mass of b, m2, is 0.08 kilograms. Okay, so really it's just a case of momentum before equals momentum after, so that's the first thing I would state. Okay, momentum before equals momentum after. Okay, then you would go into subbing. Okay, the momentum before as well, when it was A had a velocity of 3 meters per second, so it's 3 kilograms times, sorry, not 3 kilograms, sorry, 0.12 kilograms times 3 meters per second, or you could just write in your 0.36 kilogram meters per second. Plus, I know, as I said, it's tedious because it's going to end up being 0, but you need to show, just so you can correspond, you've got the same amount of masses on either side. I know you could count that, but it's very easy to get muddled up in the exam. Okay, plus 0.08 kilograms times 0 meters per second. Okay, and that is equal to the momentum after, which we know obviously the mass of A and the velocity of A, which is 0.12 kilograms times 1.2 meters per second, and then the only other thing we know that we haven't included is the mass of B, okay, which is 0.08 kilograms, and we're timesing that by its final velocity, or in other words, v meters per second. No, scrunched it on there. Okay, so what you would do is work that. Obviously, now we've got on the left-hand side, the momentum before is totaling 0.36 kilogram meters per second. Okay, our velocity on the other side, well, you just need to work out what 0.12 kilograms times 1.2 meters per second is, which should get you 0.144 kilogram meters per second. Okay, and you add that to 0.08 kilogram times v meters per second, or you could just leave it as how I wrote it there. Okay, so 0.08 kilogram meters per second. Oh, sorry. Oh, listen to me. Just kilogram times v meters per second. Okay, so then you would subtract 0.144 kilogram meters per second for both sides. So you would cancel that out and divide it, take it away from 0.36, and then divide both sides by 0.08. So your end equation for v meters per second, this is the final velocity of b, remember, so you could write v subscript b to you. So we take away 0.144 from both sides, so it's 0.36 kilogram meters per second. Take 0.144 kilogram meters per second, and because initially it was v meters per second was times by 0.08, we divide both sides by 0.08, okay, and you put kilograms there, and then that would get you a final speed for B, okay, which you should work out to be 2.7 meters per second. Okay, so we'll just write that up there. So 2.7 meters per second is the final velocity for B after this collision. Okay, just let me double check. Yep. Now, this next bit is more a logical kind of thinking question. Okay. What the question says, and I think the hardest bit of this question is understanding what it's asking you to do. Okay, it says find the magnitude of the impulse exerted on A in the collision. Basically what we're saying is, well, A has been slowed down, okay, so really the resultant would be negative, okay, be a negative impulse because it's hitting B and B is effectively taking some of this momentum away, okay, so the impulse exerted on A, if we were looking at the impulse exerted on B, then it'd be positive because B is increasing its momentum, changing momentum is impulse, okay, so it'd be increasing its momentum. Because we're decreasing A's momentum, the reason it's asked for the magnitude, whenever you hear your magnitude, just like when we were looking at the vectors and we find the magnitude of velocity at speed, okay, always becomes positive, okay, even if the vector is negative, okay, you have a negative vector, you find the magnitude and you turn it positive. That's pretty much what we do here, except we don't do any of that square rooting stuff. What we're doing is it's just saying, find the impulse and make it positive. But, you know, it's a lot more mathematical. It makes you seem smarter to say the magnitude, okay? But, you know, that's just for people who have an ego problem. Okay, so what we're doing here is working out the change in momentum of A. And it says magnitude purely because, obviously, when we work out the change in momentum, we're going to get a negative figure. Okay, so as long as you make it positive, that's the main thing. Okay, so as I said, the impulse exerted on A in the collision. Okay, well, you need to work out the change in momentum. So it's kind of like what we did in part A. You apply pretty much the same principle, except our momentum after is not 0.12 kilograms times 3 meters per second. In fact, for part C, it is 1.2 meters per second times 0.12 kilograms, or 0.12 kilograms times 1.2 meters per second. Same thing, just a different way around. Take the initial momentum, which before the collision was the final momentum of this. So in other words, the change in momentum, so this is for part C, is the momentum after, take the momentum before. In other words, the momentum after was 0.144 kilogram meters per second. Okay, and you take that away from the 0.36 kilogram meters per second. Okay, which should get you minus 0.216 kilogram meters per second. But because it's asked for the magnitude, we simply turn that positive, okay? Because it's not asking how much it's changed in terms of the actual negative. So it's what specifically how much has it changed by? What are the difference in the numbers? We're not bothered with the negative. What's the difference? Okay, so that would have been exactly the same answer for, well, what's the momentum exerted on B by A? But they've just said it a different way round. And the reason that you can apply that theorem is because, well, B had an initial momentum of 0, so the only momentum it's gained is the loss of momentum that A has given it, okay? Because remember, the total momentum before equals the total momentum afterwards. And in our system, we're only containing A and B. Okay, it's two particles. Okay, so really, all this momentum has been transferred to B. So they could have asked another question for a single mark. They might have asked part D and said, okay, well, what, therefore, using this answer, they might have even said that, calculate the impulse of B, okay? Or the change of momentum, the impulse that has been exerted by A on B, which would just be this 0.216 kilogram meters per second. Because remember, momentum is always conserved. So basically at the start, A had all the momentum and it shared a bit of it with B. So the loss that A has sustained, the loss of momentum that A has been, has come to, has all been given to B. It's not been lost to anything else. Okay, and really that's the nuts and crannies of question 2. Okay, so really, I've done quite a lot on that question for you, and it was only worth 7 marks, so nothing too spectacular, but still quite a weighty question. Okay, so thanks for watching, and hopefully we'll see you in the next video.